Hello everyone, I am Parvati Angdi, Department of Electronic and Communication Engineering from Sri Venkateshwara College of Engineering in Bangalore. Today I am going to discuss about eigenvalue and eigenvectors. Introduction to eigenvalues and eigenvectors. Eigenvalues and eigenvectors are fundamental concepts in linear algebra. They play a crucial role in various areas such as physics, engineering, and data analysis. Understanding eigenvalues and eigenvectors helps in solving system of linear equations and analyzing the behavior of linear transformations. Definition of eigenvalues and eigenvectors. Eigenvalues are scalar values that represent the scaling factor by which an eigenvector is stretched or compressed. Eigenvectors are non-zero vectors that remain in the same direction after a linear transformation, only being scaled by their corresponding eigenvalues. Eigenvalues and eigenvectors are always found together as a pair. Calculation of eigenvalues and eigenvectors. To find the eigenvalues and eigenvectors of a matrix, we solve the equation A minus lambda I into V is equal to 0, where A is the matrix, lambda is the eigenvalue, I is the identity matrix, and V is the eigenvector. This equation is known as the eigenvalue equation or characteristics equation. The solution to this equation gives us the eigenvalues and eigenvectors of the matrix. Properties of eigenvalues and eigenvectors. Eigenvalues can be real or complex numbers. Eigenvectors corresponding to different eigenvalues are linearly independent. The sum of the eigenvalues of a matrix is equal to the trace of the matrix, while the product of the eigenvalues is equal to the determinant of the matrix. Geometric interpretation of eigenvectors. Eigenvectors represent the directions of special lines or planes in a transformation. If a matrix represents a stretch or compression transformation, the eigenvectors point in the direction of the stretching or compression. Eigenvectors can also represent rotation or reflection transformations. Multiplicity of eigenvalues. Eigenvalues may have multiplicity, which is the number of linearly independent eigenvectors associated with a particular eigenvalue. The multiplicity of an eigenvalue can be determined by the algebraic and geometric multiplicity. The algebraic multiplicity is the number of times an eigenvalue appears as the root of the characteristics equation, while the geometric multiplicity is the dimension of the eigenspace associated with the eigenvalue. Diagonalization of matrices. Diagonalization is the process of the expressing a matrix as a product of three matrices P, D and P power of minus 1, where P is matrix whose columns are the eigenvectors of A. D is a diagonal matrix with the eigenvalue of A as its diagonal entries, and P power of minus 1 is the inverse of P. Diagonalization allows for easier computations of powers of the matrix. Matrix exponential and solving systems of linear differential equations. Not all matrices are diagonalizable, and the condition for diagonalizability is that the matrix must have linearly independent eigenvectors. Application of eigenvalue and eigenvectors. Principal component analysis. PCA is a dimensionality reduction technique that uses eigenvectors and eigenvalue to transform a high dimensional data set into a lower dimensional space while preserving the most important information. The eigenvectors of the matrix of the dataset represent the principal components which capture the directions of maximum variance. The eigenvalues represent the amount of variance explained by each principal component, allowing for data visualization and analysis. Application of eigenvalues and eigenvectors. Quantum mechanics. In quantum mechanics, eigenvectors represent the states of a system and eigenvalues represent the possible outcomes of a measurement. The which describes the behavior of quantum particles involves finding the eigenvalues and eigenvectors of the Hamiltonian operation. The probabilities of different outcomes in quantum measurements are determined by the squared magnitudes of the coefficient of the eigenvectors in the wave function. Conclusion. Eigenvalues and eigenvectors are powerful tools in linear algebra with application in various fields. They provide insights into the behavior of linear transformation, allowing for easier computation analysis. Understanding eigenvalues and eigenvectors is essential for advanced mathematical and scientific studies. Thank you.